We're now going to take a detailed look at compounds. And to understand compounds, we've also got to understand molecules and ions. These are the particles that make up compounds. Now, we've previously looked at compounds, and we know that compounds are made of two or more elements in an unchanging ratio. We also know that compounds are one of the pure substances, the others are elements, and as a pure substance, a specific compound is not only going to have the same composition, but it's also going to have unchanging chemical and physical properties. So let's take a look at two compounds that we deal with in our everyday life, table salt and table sugar. And let's look at the elements that make up these compounds. Table salt has the formula NaCl. And if we look at the periodic table, here's Na, it's an alkali metal, and here's chlorine, it is a halogen. Sodium, we know as all alkali metals, are very, very reactive. They will catch on fire with contact with water. So if we were to eat sodium, the sodium would eat away our mouth. Chlorine is a pale yellow gas, very reactive and very poisonous. It's one of the components of mustard gas. However, when these two elements combine, this metal and this nonmetal, what we come up with is a white crystalline solid that is extremely unreactive, and not only is it unreactive, but it's the opposite of poisonous. All life needs sodium in their cells to keep the electrolyte balance where it needs to be. So there's no way we could tell by looking at this white crystalline solid what the elements are that make it up. Its properties are completely different than the elements that make it up. Now let's look at another compound, table sugar, otherwise known as sucrose, and here's its chemical formula. 12 carbons for 22 hydrogens and 11 oxygens. These atoms are combined in a very specific way for a specific geometry of the molecule. Let's also look at the periodic table. Sugar is made up of carbon, oxygen, and hydrogen. These are all nonmetals. And we're going to see there's a big difference between compounds that are made of nonmetals and compounds that are made of metals and nonmetals. So two different types of compounds, those that are made of only of nonmetals, like table sugar, and those that are made of metals and nonmetals, like table salt. So again, let's take a look at the individual characteristics of each element. Carbon can exist in two different forms, either as graphite, which is what pencil lead is made up of, or diamonds. Hydrogen is a very reactive, flammable, colorless gas, and oxygen, we know, is also a colorless gas. However, when all three of these elements combine in a specific way to form sucrose, we get a white crystalline solid, very much looking like this table salt, that is edible, unlike any of these elements. So again, the bottom line is the properties of the compound that forms from the elements are very different than those of the elements themselves, and we cannot look at the physical or chemical properties of a compound and determine what elements make it up. We'd have to do another type of chemical reaction to decompose it, is what it's called, to figure out what elements make up a given compound. Now, we've already been introduced to this law of constant composition, but it is so very important that we're going to review it again. We know that all pure substances have constant composition, and if we take any type of sample of a pure substance, then the elements are going to be in the same percentages. So this down here is water. I guess it's a water balloon bursting. That's the only thing that I can see. But no matter where we take the water from, here, there are always going to be two hydrogens for one oxygen. Water is a compound and a pure substance. This balloon here is filled with a mixture. Air is a mixture. made up of nitrogen and oxygen molecules mainly. Oh, I'm sorry, the red is oxygen. Oxygen and nitrogen molecules mainly. If we take samples of air in different places around the world, or even different places in the state, the composition is going to vary slightly. There will be addition of pollutants, the amount of carbon dioxide, water, and even somewhat the ratio between nitrogen and oxygen may vary slightly. So mixtures have variable composition. Another example of mixtures having variable composition is gasoline. When you go to the gas station, there are 3 different types, sometimes more if you have diesel, types of gasoline. What makes them different? They have different composition, but they're all gasoline. So that's a mixture. Another example would be milk. When you go to the grocery store, there are several different types of milks, but they are all milk. They are mixtures because each different type has a variable composition. Whole milk has a different composition than skim milk, but it's still considered milk. Now, because of the constant composition of compounds, and because elements have unchanging masses, and remember the masses are the weighted average of the isotopes that make them up, we can look at the mass ratio of elements to one another in any compound and will always be the same. So let's look at this example. What am I talking about? If we decompose water, and that means break it down in chemical terms, by electrolysis, water is very, very unreactive, but we can break it down into its elements by shooting an electric current through it. We find 16 grams of oxygen to every 2 grams of hydrogen. And no matter what amount of water we decompose, we will always find this ratio to be true, 16 to 2, or 8 to 1 of oxygen to hydrogen. So pause the lecture and take a second to show that hematite, which is a compound, has constant composition. And let's look at the 2 bits of information that are given to us. The first is a 10-gram sample has 7.2 grams of iron and the rest is oxygen. The other piece of information is a second sample has 18.1 grams of iron and 6.9 grams of oxygen. So let's look at what we're given. In the 2 hematite samples, we're given that sample 1 has 10 grams total, 7.2 grams is iron, the rest is oxygen, and in sample 2 we have 18.1 grams of iron and 6.91 grams of oxygen. The first thing we need to do if we're going to check the ratios of both is figure out how many grams of oxygen, and we know that the sum of these 2 have to equal 10. So I'm going to subtract 7.2 from 10, and 2.8 grams of oxygen. Okay, so let's put that in there in red because we calculated that. Okay, now let's look at our ratios. When you are looking at ratios, it is easier to put the larger number in the numerator. It just makes more intuitive sense when we look at the final answer. For our purposes, it really doesn't matter which one is in the numerator and which one's in the denominator, as long as you're consistent in both cases. But I always find it easier to put the larger number on top. So I have more iron in both cases than oxygen. So 7.2 grams of iron, and then I'm going to put that over 2.8 grams of oxygen. And if this is a compound, then sample 2 should have the exact same ratio. Now my grams are going to cancel out, and I'm going to let my calculator tell me the answers. And let's see, I get 2.57 here, and I get 2.61 here. Now let's look at sig figs and units. First, when I look at this, I only have 2 sig figs in each, so my final answer can only be 2.6. And then I'm going to be looking at iron per oxygen as my final unit, because my iron and my oxygen didn't cancel out. So there's 2.6 grams of iron per grams of oxygen. And then over here, I have 3 sig figs in each. So I can leave this ratio as it is. But to compare, I want to look at just 2 sig figs. So to the significant figures that were given, these ratios are correct. It's iron to oxygen. So 2.6 iron to oxygen, 2.61, and if we look at our sig figs, within the sig figs that were given, these ratios are the same.